Hello students, welcome to this lecture. In the last lecture, we discussed about the variational principle, its justification, how we can use the variational principle, the strategy of a variational calculation, and also we discussed how we can use variational principle for excited states, what are the limitations in those cases. In today's class, we will take some examples and see how you can use variational principle and obtain meaningful results from this method. That is what we are going to do next. The first example that we are going to take is that of a harmonic oscillator. So, when I say harmonic oscillator, I of course can quickly write down the Hamiltonian. I have got the kinetic energy operator and the potential energy. The potential energy is given by a harmonic potential. So, which you know that half k x square, the k being the spring constant of the harmonic oscillator, which I am expressing as m omega square. M is the mass of the oscillator, omega is its angular frequency. So, given this Hamiltonian, given this Hamiltonian, we actually can, or we in fact have seen that its exact solution is possible, and we have a fairly good idea about the eigenfunctions and the eigenvalues of harmonic oscillator problem. But then why are we trying to do this using an approximate method? The reason is the following. When we are using a new method which provides approximate solution to complex problems, it makes sense to see whether this new method, the approximate method, can reproduce the exact solution of an exactly solvable model. So, in that sense, this is actually our benchmarking test. We see whether variational principle does indeed reproduce the exact solution of this harmonic oscillator problem. Now, what we are trying to do is that we are making a guess function at the trial function phi. This index alpha on this phi says that this is a trial function which depends on this parameter alpha independently to be obtained. We have to obtain its best value. So, this trial function we are writing down as a Gaussian function e to the power minus alpha x square, and we are pretending we do not know this value of alpha. In fact, we actually know for the ground state wave function what exactly is the value of alpha if we write this form of the wave function, because the ground state wave function of harmonic oscillator is indeed a Gaussian function. So, therefore, we know the exact value of alpha, but we will try to see whether the variational principle gives us that value of alpha or not. That is the idea of this exercise. Now, if this is my trial wave function, what should I do next? There are a few fixed steps that we have to follow in variational principle. The first step is to make sure that the trial function is normalized. If it is not, then we have to evaluate this overlap integral, the overlap of the trial function with itself. When I try to do this, I see that the function is e to the power minus alpha square. So, I have to solve this integral e to the power minus 2 alpha square dx from minus infinity to plus infinity. So, in this exercise, also in future discussions, you would find that there are several complicated functions which we have to integrate. Of course, it's a very good idea actually to spend some time in doing the integration so that we gain experience, but for this course we would actually not do them step by step. Rather, I would give you some indication as to how you can solve them, which formulas should you use, which methods should you use, and perhaps at the end of the course I provide you with all the steps of the mathematical work that has gone behind these integral evaluations. But so far as this particular integral is concerned, you see we can use this standard relation to obtain the value of this integral. Okay. So, I am assuming that one does this exercise, and when you do it, you will find that the outcome is pi by 2 alpha. under square root. So, what is important here to consider is that of course, pi and 2 are constants. The overlap function depends on alpha. That makes sense because I have still this my trial function has this parameter alpha whose best value I have to obtain. So, this still depends on alpha because I am only integrating out the x and still that is why I am left with this unknown alpha value. The second step of variational principle is obtaining this energy integral, the expectation value corresponding to the Hamiltonian operator. Now, how would I do that? So, I know that this is phi star phi the Hamiltonian. So, I am essentially evaluating this phi star Hamiltonian phi integral. When I do that, you have to remember this Hamiltonian has got two terms. The first term, the kinetic energy term, which has a second derivative with respect to x. So, that means d square by dx square has to work on e to the power minus alpha x square. So, I have to, that means I have to obtain a second derivative of e to the power minus alpha x square with respect to x and then multiply that function with the e to the power minus alpha x square. That is when I am looking at the kinetic energy part of the Hamiltonian. When I look at the potential energy part of the Hamiltonian, m omega square at constant for this integration, which I am integrating over x variable. So, therefore, I will have x square multiplied by e to the power minus 2 alpha x square. So, whether the term is from kinetic energy or from the potential energy, most both the integrations you can do by following this relation, which has x to the power 2n and e to the power minus ax square. When you integrate it from 0 to infinite, you would have this. Just to remind you that these integrations are from minus infinity to plus infinity. So, if the function is actually an odd function, then it becomes life is easy because then the result is 0. When I integrate it from minus infinity to plus infinity, but when the function is an even function, I can replace it as from 0 to infinite and multiply the value of the integral by 2 because this is an even function. So, when I integrate from minus infinity to plus infinity, it is equivalent to saying that I am integrating from 0 to infinite and multiplying this value with 2, that because the function is an even function. So, given the choice we made, the trial wave function phi, we obtain the overlap function and we are obtaining the energy integral. Once we do this, we then write down this E phi, which is the expectation value of h divided by the phi alpha overlap function. So, this E phi we obtain by dividing this quantity with this quantity, and this is what the result is. Now, this is what it is telling, that it is telling that this is the energy corresponding to phi alpha as the trial wave function. What does it depend on? It has h bar square divided by 2m constants, for the problem m is constant, and m omega square divided by 8. So, if I ignore these constants, I see I have essentially alpha plus 1 over 8 alpha. I can consider that perhaps I am using a harmonic oscillator with unit mass with unit angular frequency just to make get rid of these constant terms from my expression. So, you will see that I have alpha plus 1 over alpha type of term a relation for the energy. So, now I see that this energy E corresponding to the trial wave function is going to change when I change the value of alpha. It is often a good idea to plot this function E phi as a function of alpha. When I do that, this is what I am getting. Of course, to obtain this plot, what I have done is that I have assumed atomic unit. So, h bar is 1 and mass is 1 unit, omega is 1 unit. So, therefore, essentially I have alpha plus 1 over alpha by 2 plus 1 over 8 alpha. Or so, just to look at the functional form of the energy. So, when I see this, I can recognize the pattern of the function. This is E phi versus alpha. So, I have alpha plus 1 over alpha type of function. So, for small value of alpha, 1 over alpha term dominates because alpha is very small. So, therefore, at small value of alpha, the second term dominates. As my alpha increases, 1 over alpha becomes weaker. So, therefore, alpha, the other term starts dominating. So, I have two phases at which whether alpha dominates or where 1 over alpha dominates. So, there will be a region where actually I will have this turnover, and that region will give me the minimum. So, E phi of alpha as a function of alpha looks something like this. Now, the job is to find out the value of alpha which minimizes this energy. So, now from this plot I see that it will appear somewhere here, but mathematically how can I do? I can do that analytically by simply ensuring that if I take first derivative of this function with respect to alpha and make that as 0, then I will find out what is that value of alpha which satisfies this condition. I would when I do this, I would immediately get the result as this, m omega divided by 2 h bar. So, this is my best value of alpha which minimizes this energy. So, this value of alpha, I am calling this alpha 0 now, that minimizes the energy to some value. Now, this is when I put this alpha 0 in this wave function expression, that becomes the best description of my ground state given the trial wave function I have chosen. And when I put this alpha 0 in this energy expression, the value that I would get would tell me the best energy expression for corresponding to the choice of the trial wave function that I have made. So, these are this alpha 0 is the best case scenario corresponding to this trial wave function. Now, when you look at this, you would actually, if you plot this alpha 0, if you plug this alpha 0 value into this energy expression, you would see that it would come out, it would give you the exact ground state energy of harmonic oscillator. When you plug this alpha 0 into the wave function, you would also reproduce the exact ground state eigenfunction of the harmonic oscillator problem. But we will try to do that numerically. So, I have plotted the energy and the wave function for a series of alpha values. We will go through them. So, I see that here I am considering mass as 1, omega as 1, h bar is as 1, or in other words you can say that I am expressing this energy as in the unit of h bar omega. In that case, the true energy, the real energy is 0.5 h bar omega, because n is 0. So, half h bar omega, since I am expressing this energy in terms of h bar omega. So, this is 0.5. The dashed blue line indicates the true ground state energy. Now, when I use alpha as 0.1, then I see the energy that I am getting is somewhere here, which is an 160% overestimation of the true energy. When I change alpha to 0.3, I very quickly come much closer to the real true value of the energy, the exact solution, and the error is merely 14%. When I go to of course, when alpha is 0.5, that means in this case alpha 0 is 0.5. So, when alpha is 0.5, that is actually the best case scenario. That is what alpha 0 is. In that case, when alpha is 0.5, I reproduce exactly the true ground state energy, that is obvious here. But what is more important is that when I increase it further, alpha goes to 0.7, you see the red line. So, then also it provides me an upper bound to the true energy. So, alpha equals 0.1, the orange line, alpha equals 0.3, the green line alpha equals 0.5, that is the blue dashed line, and when I make it alpha equals 0.7, it goes up, because we see 0.1, 0.3, 0.5, they were all coming down, but when I crossed the best value of alpha 0, my energy again rises up. So, this is what the beauty of variational principle is. So, it is not a monotonically decaying function that it would go like this, but the moment you cross the best value of alpha 0 and overseed it, the energy will show up as going away from the ground state, the true energy. Now, let us look at the wave function. So, corresponding to alpha equals 0.1, you see this orange form of the function. Before that, the exact solution is given again here as a dashed blue line. You see this is the beautiful Gaussian function centered around x equals 0. So, this is the true wave function, and alpha equals 0.1 does not really match that well. The green one, alpha equals 0.3, it has better resemblance to the ground state wave function. Alpha equals 0.7, this also has a good resemblance with the ground state wave function. So, here you see alpha equals 0.3 and alpha equals 0.7, both have more or less similar resemblance to the ground state wave function, but we can see that we can distinguish them in terms of their energies, which one is better or which one is worse. But we come back to this relation between the energy and the wave function again and again in some other in another example. So, here is an example where I started with my trial function, which just looks like the real solution. So, therefore, it is no wonder that I am able to get the exact solution using variational principle. So, this proves the application of principle that if there exists a solution out there, and if I start with a very good guess, I will end up in getting the exact solution. Now, we will take another example, again that will be a harmonic oscillator problem, but the trial wave function would not be a Gaussian function, but would be something that would have overall similarities, but not exact functional form. The trial function that I am considering is 1 over x squared plus alpha. So, again alpha is the unknown whose value I am going to get using variational principle. Why should I take this function? You see, imagine when x goes to 0, I have 1 over alpha. So, it has a finite value, the wave function, and when x becomes either plus finite value or minus finite value, this function would start decaying on either side of the ordinate. So, when alpha x goes to plus values or x goes to minus value, it would start decaying from 1 over alpha value, because there in that case 1 over x square plus alpha would be less than 1 over alpha. So, overall it would actually show a function which is somewhat similar to the ground state wave function of harmonic oscillator that we have seen. At least the boundary conditions are satisfied, that x equals 0, it should have a finite value, and from away from x equals 0, the wave function should decay. How slowly or how quickly it is decaying, that is another matter, but overall function satisfies the general boundary condition. With this, again I would remind you, when I have made a trial wave function, I have essentially two important steps. One, to check the overlap of the wave function with itself, evaluate the overlap integral, or essentially normalize the function. The second is evaluate the energy integral or the expectation value. When I do the overlap integral, I obtain this term over here. Again, point to remember, the integration is something that has to be done. So, please remember, look at the function of the form of the function, and then you can make a guess as to how to integrate this function. So, the outcome of this exercise would give you some constant multiplied by alpha to the power 3 by 2. What is important to see that this function the value depends on alpha. The next step is again simple. We obtain the energy integral phi alpha h phi alpha. So, this is again a complex looking function, but do not worry, they are mostly constant except for alpha as appearing as phi by to the alpha to the power 5 by 2 here, and 1 over alpha to the power half or square root of alpha. So, again the energy term depends on alpha. So, I am evaluating the energy value as a function of alpha by dividing this quantity with this quantity, and this is the expression that I am getting. One more time, see, except for the constants like h bar or mass or angular frequency, I have only dependence on alpha. So, in fact, this function also, this energy also looks like 1 over alpha plus alpha type of term. So therefore, I know that when I minimize this function, I would have a single value of alpha where the function will become 0. When the E phi will be the first derivative of E phi will become 0. So when I do this, exercise, when I try to find out the value of alpha that minimizes the energy, I get alpha 0, or the best case scenario as 1 over root 2 h bar by m omega. So again, if I consider atomic unit h bar as 1 and m and omega are unit, I am considering unit mass and unit angular frequency just for convenience, then I see alpha 0 is 1 over root 2, which is, if you remember the previous case, we had some other value, but we will see how this alpha 0 this value of alpha 0 influences the energy. So what would I do? So what is my best energy? If I plug this value of alpha 0 into the energy value E phi, then I will get that is my best energy. What is the best wave function? If I take this value of alpha 0 and put it in the trial function, that is the best description of my ground state wave function. Now let us see what we are going to get if we do this numerically. This is what the result is. Again, the energy is expressed in this diagram, the wave function is expressed in this diagram. Energy is expressed in terms of in the units of h bar omega. So the exact solution, see this is still harmonic oscillator problem, the exact solution is the ground state energy, which is half h bar omega. So therefore 0.5, this is shown as the dashed blue line. The exact wave function is shown here, again with the dashed blue line. When alpha equals 0.1, that means a very small value of alpha. So you remember this value in the unit of m omega and h bar, when they become 1, this is simply 0.707, that is the best case scenario. When alpha is 0.1, I see this is energy, it actually overestimates the true energy by 400%. When I slowly increase the value of alpha from alpha equals 0.1 to 0.3, it approaches the true energy rapidly, and when but still the overestimation is about by 100%. When I further increase to the best case scenario, that is 0.707, you see it goes from orange to green to red. So 0.707, this gives me the best case scenario in this case, but the best case scenario is 40% off my true energy. True energy is 0.5 omega. So this is about close to 0.7 omega. So I see a significant difference over here corresponding to the true state energy, but at least I see that the energy is coming closer. Now I am overshooting the best value of alpha, that is 0.1 over root 2, and going beyond that. So I am taking another value as alpha equals 1.2. You see that from orange to red to orange to green to red, the energy was approaching closer to the true energy, but when it overshoots the best value of alpha 0 and goes further, then again you see this purple line shows that the energy is going further away. Now energy is going away from the ground state energy. So that indicates that we have crossed the best value of alpha 0, and now we are going again in the wrong direction. From orange to green to red, we are going along the correct direction, but from red to purple, we see that we are going again in the wrong direction. So variational principle actually helps us whether we are coming closer to the true solution or not. Now let us look at the corresponding wave function. Alpha equals 0.1 or 0.3, since the value of alpha is very small, so the function would actually show a peak somewhere up there. So I am not showing that. When you look at alpha equals 0.707, qualitatively it resembles the eigenfunction of a harmonic oscillator, but compare this alpha equals 0.1 alpha equals 1.2, where the energy is worse than the energy for alpha equals 0.707, the true value. So in this case you would realize that perhaps alpha equals 1.2 makes a better description of the wave function as compared to alpha equals 0.707. but energetically speaking 0.707 value of alpha is a better value, it provides better estimation of the energy compared to when alpha equals 1.2. So, there is something different going on here. This is actually often the case. You have to remember that variational principle blindly minimizes the energy. It does not have any other condition as to what it does to the wave function. In fact, it does not care. So, but the wave function contains all the informations including energy. So, energy is one manifestation that we can get out of the true wave function. But what variational principle does is it emphasizes only on the energy and tries to find that form of the trial wave function that minimizes the energy. So, the wave function that we get out of this variational principle not necessarily a great wave function for different properties. Why am I saying that? Because many other properties, you remember quantum mechanics tells that if I want to evaluate a particular property, I must bring that operator and apply it on that the state function. Now, the state function is defined by phi, which is based on a trial function that minimizes the energy, but it does not necessarily has all the qualities of the wave function so that it can give rise to all other properties. For example, if I evaluate the expectation value of even the kinetic energy or even expectation value of the potential energy, it may have a different outcome there. If I evaluate the dipole moment or any other properties, in those cases I cannot guarantee that the variational wave function that I am getting would be the best wave function to obtain those properties. But so far as energy is concerned, the variational principle works well. So, since many of our in chemistry, many of our chemical reactions, chemical reactivity we can express through energy, in that case variational principle is a wonderful way to do. Of course, the limitation that we just discussed can also be overcome, and we will discuss some of them in our future class, but you have to remember this in mind, that variational principle often gives a great estimation of energy, but many times the estimation of other properties are not so wonderful. All right. So, we now look at yet another example. This example is for hydrogen atom. So, again hydrogen atom is a problem whose exact solution we know. So, here I am writing down the Hamiltonian of the hydrogen atom. I have got the kinetic energy operator and the potential energy operator, and I am making a Gauss function as e to the power minus alpha r square. So, this is a Gaussian function. If you remember, the true solution of the hydrogen atom ground state function is e to the power minus some constant into r. So, it should decay as an exponential function as the distance between the electron and nucleus increases. But here what we are doing, we are deliberately using a wrong functional form of the trial wave function. When we are doing this wrong, taking this functional form of this eigenfunction, we can quickly go through the maths. The process is more or less similar. The first step is to evaluate the overlap integral. When I do this, I obtain this. Important thing to notice is that how it depends on the value of alpha. Second step, evaluate the energy integral, the expectation value of the Hamiltonian operator. Again, some constants with alphas over here. So, therefore, the energy E phi term is a function of alpha over here. Now, I can minimize the value of alpha to obtain the best energy. So, what is the value of alpha that minimizes the energy? And if I do this exercise just like the previous cases, I would obtain alpha 0 is equals to 8 divided by 9 pi. Now, this value of alpha 0, when I plug in the energy, I would see that I am obtaining a value of energy as minus 0.424 atomic unit. If you remember, the true energy value of the ground state energy of hydrogen atom is minus 0.5 atomic unit. So, you see that it does not provide the exact value, but let us again do this numerical exercise. with different values of alpha to find out how we are approaching the true solution. So, alpha 0 is the best value of alpha 0 is 8 over 9 pi, which turns out to be 0.283 in this case. So, in this exercise what we are doing is that we are starting from alpha equals 0.1, 0.283, 0.6, 1.2, and this is the exact solution. The exact solution we know from hydrogen atom, this is minus 0.5 atomic unit. Now, you see, you can realize that how I am, by changing my alpha values, the different energies are behaving and how they compare to with respect to the true energy. Now, look at the wave function. Again, when I consider the wave function, I see that the blue dashed line is the true solution. The solid lines are the values that I am obtaining over here in from this trial function. So, you see in most cases the trial wave functions are not able to reproduce the shape of the true wave function. That is natural, because we have taken a wrong functional form of the function. We know that the wave function should depend as e to the power minus alpha r, but we are taking e to the power minus alpha r square. So, naturally we do not expect that the wave function agreement will be so good. So, therefore, the properties that will come out of it will not that be good, but still even when we are taking a wrong functional form of the trial wave function, you can see we still can go very close to the true energy. Here in this case is minus 0.424 atomic unit. So, in this example actually gives us the idea that even when our functional form is somewhat not physically adequate, in those cases also variational principle can give us a very good estimation about the ground state energy. So, in this way, using these examples, I hope I convinced you that variational principle is a robust method to evaluate the energy of the ground state of a system. Thank you for your attention.